Welcome to Unit 3 of Cellular and Mobile Communication. So, today we will cover the entire unit. Entire unit means cell coverage for signal and traffic. So, as per the syllabus, it will cover that what happens when signals reflect in flat and hilly terrain. What is the effect on signal propagation or signal transmission due to human-made structures? It will discuss the phase difference between direct and reflected paths, the straight line path loss slope, and the general formula for mobile propagation over water and flat open area. Near and long distance propagation, antenna height, gain, and when point-to-point communication is possible between the transmitter and receiver. So what are the conditions? Unit 3 is focused on all this. So our today's goal will be to cover entire Unit 3. We will discuss each of the topics. We will discuss basic theory. We will discuss solved examples, formula, everything. So today's class might go a bit longer, but our goal is to finish this unit. So after this lecture, you will be able to explain the signal reflection in flat and hilly terrain. You will be able to describe the effect of human-made structures on mobile radio propagation. You will be able to calculate the phase difference between direct and reflected paths. You will be able to explain the straight line path loss slope. You will be able to use a general mobile propagation formula for practical applications. You will be able to explain the propagation over water and flat open area. And you will be also able to describe near distance and long distance propagation. You will be able to explain that what should be the ideal height for antenna. And finally, we'll be able to understand the basic form of a point-to-point prediction model. So with this, let us start with this topic, signal reflection in flat terrain. So in flat terrain, the signal from the base station means the tower. So two units, again, we need to keep it in mind. One is called mobile station, another is called base station. So mobile station means MS means mobile phone, our mobile phone, and base station is BS. It means the tower. So these terminologies we need to keep it in mind. Keep in mind. So in flat terrain means what? When the signal propagation is traveling through a flat landform. So signal from the base station reaches the mobile receiver mainly through two paths. One is called direct path, another is called ground reflected path. So this is the starting point of this part, that what happens when one transmitter and receiver are placed at a distance and in between there is a flat surface. So when the transmitter transmits, so it reaches the receiver in two ways. One is direct, another is reflected from the ground. So these are the two concepts. Now, if I look at the diagram for this, So you can look at this diagram that this is one mobile tower which is having a height of ht, or this is the transmitter we are assuming. So ht means the height of the transmitter, and this is the mobile station. So mobile station is having the height hr, for example. Okay. So this transmitter has a height and this mobile station has a height. Now when transmitter is transmitting, you can see that there are two ways. So one is this way, that is called direct way or direct path. Another is called reflected path. So this one is the reflected path. So in two ways, actually signal is reaching from this transmitter to receiver. There are two paths. When the signal is reaching from this transmitter to receiver through different paths, so definitely what will happen due to the path length means signal is traveling some path through this direct path and signal is traveling some another path through this reflected path. So signal is actually traveling two different path. Now when a signal is traveling two different path, so there is a relationship between the phase difference due to that traveled path difference. So what is the formula? So the formula is phase difference is equal to 2 pi by lambda into path difference. So phase difference means delta phi, this is the phase difference, is equal to 2 pi by lambda into path difference. This is a standard formula that we know since our school days. Okay, that phase difference is equal to 2 pi by lambda into path difference. So as there exists some path difference between this direct path and this ground reflected path, so definitely there will be some phase difference. Now if the phase difference among this phase difference between these two components are zero or in the multiple of 2 pi. So 2 pi means 360 degree. So if the phase difference between these two paths are either 0 or 360 degree, then we will say that these two signals are in phase. In phase means they are effectively have traveled the similar phase. The second case might be they are out of phase. Out of phase means this phase and this phase have difference of 180 degree. So this is called out of phase. If the two signals are out of phase, then what will happen? They will cancel. Okay, they will cancel each other. When they cancel each other, then the received signal will be very less or very weak. If they cancel each other being out of phase, then we will be observing some dead zone. These are dead zone. It means signal amplitude is very low. And if they get added in phase, then we will get some signal spikes, or it will be added. So two types of interference may occur. Either this is additive or subtractive. So if they're additive, then we will get spike. If they're subtractive, then we will get dead zones. Okay. So now, so the key formula is path difference is equal to 2 pi by lambda. A phase difference is equal to 2 pi by lambda into path difference. So this is our formula. Now let us focus on some solved examples. So in the solved example, it is given that a direct path and reflected path have a phase path difference of 0.25 meter. That is given in the question paper. So direct path and reflected path have a path difference of 0.25 meter. It means delta D is given, that is 0.25 meter. The wavelength is 0.5 meter. It means the lambda is given 0.5 meter. So find the phase difference. So we need to calculate del phi. So del D is given, lambda is given, and we need to find del phi. So we know that the phase difference is equal to 2 pi by lambda into path difference. So if I substitute the value, then del phi will be equal to 2 pi divided by 0.5 into 0.25. Both units are in meter. So now the answer will be delta phi is equal to 2 pi into 0.5 and the unit will be radian, because we have computed only these pi's and all these things. So del phi value will be 3.1 for radian. So always remember that whenever some expression are containing pi for calculation of angle, always the unit will be radian by default. It will not be degree. So we know that what is the relationship between radian and degree? So 180 degree is equal to pi radian. So 180 degree is equal to pi radian. So 1 radian is equal to 180 degree divided by pi. So if my answer is 3.1 for rad, so I can convert this to degree by 3.14 into 180 degree divided by 180 degree divided by pi. So if I do that, then I will get the answer. Now pi means 3.14. So 3.14 this cut, then 180 degree. So also we have got here pi radian. So pi radian means 180 degree. So always whenever you are getting any answer in radian, so try to replace the value if you want to convert it to degree. But the direct calculation will be in radian itself. Now phase difference between direct and reflected paths. So in the two-ray model, we have already experienced that the direct wave and reflected wave, they travel different distances. For large separation distances, the path difference can be approximated using antenna heights and distance. Now, what is the formula? The formula is delta D, or the path difference, is equal to 2h1 h2 divided by D. That can be approximated if the heights of the transmitter and receiver are known. Suppose phase difference is not known directly. So heights of the transmitter and receiver are known. So from that we can calculate the path difference directly. So if the path difference is known, then we know that the phase difference del phi is equal to 2 pi by lambda into path difference. So if I replace this value in this equation, okay, then we can get this expression that del phi is equal to, if I simply put this, so if I simply put this delta d here, then we will get this expression, that 4 pi h1 h2 divided by lambda d. So very simple equations. Now what is h1? So h1 means the base station antenna height. H2 means mobile antenna height. D means distance between transmitter and receiver. Lambda is the wavelength. So let us solve another example. So it is given that H1 is equal to 30 meter. It means the base station antenna height is 30 meter. H2 or mobile antenna height, that is 3 meter. All the mobile phone is at a height of 3 meter from the ground. D is 8,000 meter and lambda is equal to 0.353 meter. Suppose this information are given. And the question is find the phase difference then. Now from all these given values, so if I write the formula, that formula we already deduced. So del phi approximately equal to 4 pi h1 h2 divided by lambda d. Okay. Now if I know h1, I know h2, I know lambda, I know d, everything I know. So if I simply substitute the values, then finally it will come in radian. Okay. So the answer is 360 pi. So 360 pi is the numerator. So from the numerator we get 360 pi. So if I further calculate the denominator and divide, so finally I get the answer del phi approximately equal to 0.4 radian. Now what will be the radian to degree, this conversion? So I have told that 1 radian, pi radian is equal to 180 degree. So 1 radian is equal to 180 degree by pi. So for 0.4 radian, this will be 0.4 into 180 degree divided by pi. And we can get the value in degree. So till now we have learned a very nice set of equations related to phase difference and path difference. So just we need to remember to attempt problems and to get the answer quickly. Okay, now several times we may need to convert the frequency to wavelength or vice versa, because sometimes lambda might not be given, frequency might be given, and from that you need to calculate lambda. So in some problems it might come like that as well. So we know that lambda is equal to c by f in when the wave is propagating through the free space. So lambda is equal to c by f. So c is the speed of light or any electromagnetic signal through vacuum or air. Now, as mobile telephony means there is an electromagnetic signal, so that is why we will be taking 3 into 10 to the power 8 meter per second. So sometimes lambda will not be given directly, frequency will be given, and from that you need to calculate lambda. So for example, find out the wavelength for a frequency 850 megahertz. So how to do that? So we know that c is equal to 3 into 10 to the power 8 meter per second. So that is why I am writing 3 into 10 to the power 8. And 850 megahertz, so 850 into 10 to the power 6. So definitely this unit will be meter. Now after that, if I solve this, then I will get 0.353 meter. So in this case, suppose in the previous expression, so what was the previous expression? Del phi is equal to 2 pi by lambda into delta d. This was a formula. Now, suppose lambda is not given, f is given. So we know that 2 pi divided by lambda is equal to, what is lambda expression? Lambda is equal to c by f. So c by f into delta d. Okay. Now c by f. So 2 pi f divided by c into delta d. So when lambda is not given directly, so we can also use this formula to get the value of the phase difference. Now what is the received power in this two-way propagation? So when power is getting received by a mobile receiver, and h1 means already we know that is the height of the transmitter or base station, and h2 is the height of the mobile station. So then the received power will be PR, that equal to P0 into H1 H2 by D2 whole square. So this is the formula for this. Now if I expand this, so definitely this will be P0 into H1 square plus H2 square, H1 square into H2 square, sorry, H1 square into H2 square divided by D to the power 4. Okay. So if I assume that for any instance of time, H1 is constant, H2 is constant, and suppose P0 is constant, then this received power will be inversely proportional to d to the power 4. This is very important observation, that this received power is inversely proportional to d to the power 4. So what is the meaning of this? It means that the distance vector is very sensitive in power reception. Okay. So let us take one example. So suppose P0. What is P0? P0 is reference power factor. So reference power factor by default it should be 1. So suppose P0 is equal to 1, H1 is equal to 50 meter, H2 is equal to 2 meter, D is equal to 1000 meter. Suppose this is the example that is given. Now in this case, we need to calculate the receipt power. So receipt power PR is equal to P0 into H1 H2 divided by D square. Then its square, whole square, H1 H2 by D square. This is whole square. So if I substitute the value, then we get one into 10 to the power minus 8. Okay. So this is the power that we will receive. Now the next part is the straight line path law slope. So what is the meaning of this? So I have already told that the receive power decreases approximately as d to the power minus 4. Okay. So if the distance increases 10 times, the receive power decreases by 40 dB. In other terms, it can also be told like the path loss slope is about 40 dB per decade. Per decade means 10 times. Okay. So if the distance increases 10 times, the receive power decreases by about 40 dB. That is the meaning of straight line path loss slope. So what is the formula? Formula is delta P is equal to 40 log D1 by D2. So find the change in receive power. If the problem comes like that, find the change in receive power when the distance increases from 1 kilometer to 2 kilometers. So earlier the distance between transmitter and receiver was 1 kilometer. So there was some power that was received. But now the distance is changed from 1 kilometer to 2 kilometer. Then what will be the change in power? So delta P is equal to 40 log D1 by D2. So if I substitute the value, so D1 was first 1 kilometer, so I write 1 and D2 was 2. So if I calculate this, so delta P comes out as minus 12.04 dB. It means when the distance between the transmitter and receiver is separated by 1 kilometer, the receive power decreases by 12 dB. That is the significance of this. Now the next topic is the base station antenna height gain. So what is base station antenna height gain? If I increase the base station antenna height, then the signal reception is improved. So in this model, if I double the base station antenna height, so it will give approximately 6 dB gain. So what is the formula? Formula is this one, that delta G, it means the gain difference, is equal to 20 log H1 dash divided by H1. So H1 means the height of base station antenna. So H1 is the old height, H1 prime or H1 dash is the new height. So the gain difference is equal to 20 log H1 dash divided by H1. So let us take another example for this. So the base station antenna height is increased from 50 feet to 100 feet. So by increasing this height, what is the increment in antenna gain? This is the question. So first we write the formula. Delta G is equal to 20 log H1 dash divided by H1. So delta G is equal to 20 log 100 divided by 50. So finally this is 6.02 dB, or delta G approximately equal to 6 dB. Next is, suppose the base station antenna height will remain as it is. What should be the mobile antenna height gain? So increasing the mobile antenna also improves the receive signal strength. However, the gain is less than that of a base station antenna height. So doubling the mobile antenna height gives approximately 3 dB gain. So that is why the mobile antenna height gain is equal to 10 log. See, earlier it was 20 log. Now this is 10 log. So 10 log H2 dash divided by H2. So that is why we have observed that suppose we are not getting a good signal in the ground floor. So if I go in the first floor or second floor, so we get some good signal quality sometimes. So anyways, so suppose the mobile antenna height is increased from 5 feet to 10 feet. Find out the height gain. So delta G is equal to 10 log H2 dash divided by H2. So H2 is the current height, H2 dash is the new height. So if I put the values like that, then we will simply get this is as 3 dB. Okay. So for this logarithmic calculation, these are very easy logarithmic calculations. But because for this problem, it is coming very easily. But I advise that please bring your calculator in the exam hall so that you can get the problems done very easily. Whatever be the dB values and all, so you can get it done in a correct manner. Now let us come to the general formula for mobile propagation. So this is a general formula combining all the effects that we have discussed. Because the received power in mobile radio environment depends on many factors like transmitted power, distance, antenna heights, antenna gains, and the surrounding environment. So from this, it would be wise to use a general formula that will include all the effects. So there is an equation. You can see the equation PR means received power is equal to PT minus K minus gamma log R1 plus 20 log H1 plus 10 log H2 plus GT plus GM. There is one formula. So PR, it means the received power in dBm. PT means transmitted power in dBm. So K is an environment dependent constant. So this constant value is 157.7 for suburban area. So if some problem comes in the examination, we can assume this value in for suburban area, And the path loss slope factor is 38.4. So this is commonly used in suburban area. R1 is the distance, H1 is the base station antenna height, H2 is the mobile antenna height, GT is the transmitting antenna gain, and GM is the mobile antenna gain. So these are the meaning of all these symbols that have been used here. So now, if I substitute the value of K, so definitely in equation it will come 157.7. And if I substitute gamma, so definitely it will come 38.4 here. And rest of the values will be given, and based on that, you need to calculate. So one important point is whenever you will be given some problem to solve on this, so this environment dependent constant values and path loss slope factor that you need to remember. So let us solve one problem. So it is given that the transmitted power is 40 dBm. R1 means that distance is 2 miles. Okay. H1 is 100 feet. H2 is 10 feet. GT is equal to 6 dB and GM is equal to 0 dB. So we will simply apply this formula. And finally, we will get this PR is equal to minus 73.26 dBm. The next topic is propagation over water and flat open area. Now, when a wave, so why this propagation over water and flat open area is so special? So because when in a suburban environment, when any wave is hitting the ground is a rough surface. So when the wave is hitting on the ground, so some amount of scattering happens, so that instead of going towards the mobile station, the wave is scattered here and there. But when the wave is propagated over water and flat open area, so reflected waves can be very strong, because being the reflecting surface smooth, the scattering is less. So this is similar way like some two-ray pathway model. So based on the phase difference between among the components at the receiver, so we can decide whether this is constructive or destructive interference. So this is the formula. I'm not reading out the formula. You can go through the formula also. So let us solve another problem. So PT is equal to 10 watt, D is equal to 1000 meter, and lambda is equal to 0.3 meter. So if I find the received power using the simplified expression and put the values over there, so finally we will get the value in nanowatt. So 5.7 nanowatt is the answer for this. Now point-to-point model. So point-to-point model predicts the received signal strength for a specific transmitter receiver path, because when we are designing some system, so we use a point-to-point model only for simplicity. So it considers distance, antenna gains, propagation loss, and additional losses. Okay. So there might be some scattering, say there might be some diffraction, etc. So through ray tracing path, it is not considered. So a total loss is considered as additional losses or obstruction losses. But the model remains point to point. So suppose this is some base station and some um, mobile station is there. So in between there could be some building, there could be some hills. So all falls under the obstruction or environmental loss factors. So the formula is PR means the received power, PT plus GT, it means the transmitted power plus gain of the antenna, plus GR, receive antenna gain, minus LP, LP means path loss, and L0 means additional loss. So all these values are given in dB and dBm. So if the values are given dB and dBm, then only we can use this equation where the received power is a simple addition and subtraction of the different power components, because the units are given in the logarithmic scale. Okay. So anyways, if I simply put the values, so this could be 40 plus 10 plus 2 minus 120 minus 8. So if I finally calculate this, so finally it comes as minus 76 dBm. Now let us come to, so we have discussed different types of mobile propagation models. So first we started with a free space propagation model. So satellite links are there, microwave line of sight links are there. Okay, ideal open area reference are there. It means between transmitter and receiver, there is only a free space. So the main use for this free space propagation model is the basic receive power estimation. But it is not suitable for cellular and mobile environment, because in mobile, cellular and mobile environment, there are buildings, terrain, multipath, all these factors are there, which are not in the scope of free space propagation model. Now comes the basic model that is used for our urban or suburban telecommunication. So two-ray ground reflection model. So with this, we started today's lecture. So this is a open field, flat terrain, okay, highway communication oriented model. It can be used in rural mobile coverage also, because be it rural, suburban or urban, whenever there is a transmitter, whenever there is a receiver, so this two-ray model is universal. Now in urban or hilly areas, what happens? These could be more than two rays, because the points of diffraction, reflection increases. Okay. So that is why this two-ray ground reflection model could be a basic model for all the situations. But if we need more accuracy, then it is good for rural mobile coverage, because obstructions are less there, but less accurate in urban or hilly areas. Now let us come to the propagation over water and flat open area model. So suppose I am developing my cellular coverage plan for some coastal area, some seaside, lakeside area. Okay. So for that, this propagation over water or flat area open model is useful. But this model is very inaccurate for dense urban areas. Now straight line path loss model. So straight line path loss model, it's a general cellular coverage estimation because all other losses are actually assumed as a value like other losses, LO, and it gives some average range only. Now general mobile propagation formula. So for this, the constants needs to be selected carefully, like the constant of K 157.7 for suburban. So that value will change if this is a highly dense urban or very lightly dense village area or rural area. So near distance propagation model. So when the coverage is very close to the base station, and if we can use this for microcell planning and for small cell design. And the far distance path loss formula may not be applied here accurately. And finally, the long distance propagation model. So long distance propagation model is strongly affected by the atmosphere, terrain, and unusual propagation conditions. And the antenna height gain model. So what is the effect of increasing antenna height in mobile signal coverage? So sometimes what happens that we have seen that the gain increases if we increase the antenna height. But also we have studied in our previous lecture that if I increase the antenna height beyond some point, then the radiation will reach to some cells, I mean, where interference will be very high. Co-channel interference or adjacent channel interference will be high. Now, point-to-point prediction model. So detailed site-specific cellular planning is done or carried out through this model. So it can cover holes, hilly terrain, obstruction analysis. So in this case, all other losses needs to be tackled very carefully. And finally, we need to calculate what is the total amount of losses due to different factors. So what was our point of learning today? So mobile radio propagation is affected by reflection, diffraction, terrain, antenna height, and human-made structures. In flat terrain, direct and reflected waves combine at the receiver. It means the two-ray propagation model. In hilly terrain, the hills may block, reflect, or diffract the signal. Now, human-made structures create shadowing and multipath. The phase difference between direct and reflected waves depends on path difference and wavelength. In the two-ray case, the receive power varies approximately as d to the power -4 or inversely proportional to d to the power 4 that we have discussed. It gives a 40 dB per decade path loss slope. It means if I increase the distance between transmitter and receiver 10 times, then the receive power will be dropped by 40 dB. That is the meaning of this. Now, increasing the base station antenna height gives out 6 dB gain per doubling, but increasing the mobile antenna height gives about 3 dB gain only per doubling the distance. So a point-to-point model estimates the receive power for a specific path using transmitted power, antenna gains, path loss, and obstruction loss. So for point-to-point model, before applying the model, we need to estimate different types of losses very carefully.